So hello students, in this video we are going to learn about entropy. We'll learn how to determine entropy change in different processes. So let us start with few fundamental concepts of entropy first. We are going to talk about only the mathematical form of entropy, not the logical form of entropy. So mathematically, entropy is defined in a reversible process. Entropy is defined in a reversible process. Does not mean that in irreversible process entropy does not change. So it is defined in a reversible process for one infinitesimal step as ds is equal to dq reversible by t. So entropy is defined in reversible process. It is not defined in irreversible process. Although it changes in all kind of processes, but it is defined in a reversible process. That is one thing. So total entropy change in a process will be integration of this ds, which will be delta s, which will be integration of dq reversible divided by t. Now from the first law we know that dq reversible for a reversible process is du plus pdv divided by t, this whole integration. Du, change in internal energy, is cv dt, so it is integration of cv dt, sorry, ncv dt for n mole, ncv dt by t plus substitute py nRT by v, so p is equal to nRT by v, tt will cancel out, so nr dv on v. Now separate the two terms, so first term will be ncv integration of dt by t with temperature limit T1 T2, and the second term is nr dv upon v integration volume limit V1 to V2. So if we integrate it, it will come out to be ncv log natural T2 by T1 plus nr log natural V2 by V1. We can also substitute v by nRT by p, and if we do that, this will also be derived in the form of Cp, so it will be ncp ln T2 by T1 plus nr ln of P1 by P2. So that is the expression for delta S in terms of temperature, volume and pressure. We derived this expression assuming the process to be reversible. Once it is derived, this expression of entropy change is applicable to any process, whether it is reversible or irreversible, because entropy is a state function. So change in entropy delta S does not depend on path. So using these two expressions, we can determine entropy change for a system in any process. That is one thing. Now, the point here is, how do we determine entropy change for universe, which include system and surrounding. So the point we want to understand here is how to determine entropy change for universe. So delta S universe is sum of delta S system plus delta S surrounding. Why we want to know delta S universe? Because according to second law of thermodynamics, a spontaneous process leads to increase in entropy of universe. So if we can determine the delta S universe for a process, we can predict whether the process will be spontaneous or non-spontaneous. Now, how to know delta S universe? Delta S system can be determined as we derive the expression. What about delta S surrounding? See, if the process is reversible. If the process is reversible, then we can say that delta S system will be equal to Q system by T. Since the process is reversible, so Q system will also be Q reversible divided by T will be delta S. Also, Q surrounding will be equal to minus Q system. So delta S surrounding will be Q surrounding divided by T, which is minus Q system divided by T. So delta S universe can be determined using the above two expression. Delta S system is Q system by T plus delta S surrounding is minus Q system by T. And these two terms will cancel out to give 0. So if the process is reversible, the entropy change of universe will be 0. Based on that, we conclude that if the process is reversible, system always remain in equilibrium with the surrounding. What about irreversible process? Suppose the process is irreversible. If the process is irreversible, in that case Q system is not Q reversible. Q system is not Q reversible, so delta S will not be equal to Q system by T. It will not be equal to Q system by T. Now delta S will be determined using the expression we derived. So now delta S system will be equal to NCV ln of T2 by T1 plus NR ln of V2 by V1 or the other expression NCP ln T2 by T1 plus NR ln T1 by T2. Now what about delta S surrounding? Now delta S surrounding, how to know? For determining delta S of surrounding, we must be aware about one thing, that reversible, irreversible change are the case for system only. Surrounding is the infinitely big, and therefore all change in surrounding occur reversibly. So changes in surrounding occur reversibly. There is no irreversible process in surrounding. Irreversible can be in the system only. So delta S surrounding can always be written as Q surrounding divided by T, because Q surrounding will always be Q reversible. And now Q surrounding will be minus Q system. Be very careful that for system this is Q system is not reversible, but for surrounding minus Q system, which is Q surrounding, will become reversible heat, and therefore for surrounding we can always determine entropy change equal to Q surrounding by T, and Q surrounding will always be minus Q system. Now let us apply this for solving a numerical question. We would be better in understanding this concept. So suppose we have been given that 1 mole of an ideal gas in a piston at 300 Kelvin and 10 atmosphere undergoes isothermal expansion against a constant pressure of 1 atmosphere till the gas pressure decreases to 1 atmosphere. 1 atmosphere. Determine delta S system, delta S surrounding, and delta S universe. This question is related to irreversible isothermal expansion of gas. Why irreversible? Against a constant pressure of 1 atmosphere. External pressure is constant, so the process is irreversible. And for this process, delta S cannot be determined as Q system by T. Delta S will be determined by the expression we derived. So delta S system will be equal to NCV ln T2 by T1 plus NR ln V2 by V1 or NCP ln T2 by T1 plus NR ln P1 by P2. Since the process is isothermal, T2 is equal to T1, so this term will vanish. P1 is 1 atmosphere and P1 is 10 atmosphere and P2 is 1 atmosphere. N is 1 mole. So it is simply R ln 10, and ln 10 is 2.3. So it is 2.3 R. This is the entropy change for system. Now, what about surrounding? Now, delta S surrounding will be equal to Q surrounding by T, which is minus Q system by T. Then how to find minus Q system? We'll apply first law. So according to first law, in irreversible isothermal process, Q system is equal to minus Px. Q system is equal to P external delta V, and delta V is now V2 minus V1. So it is P external V2 minus V1. V can be substituted by nRT by P. So P external nRT 1 by P2 minus 1 by P1. So it is nRT P external upon P2 minus P external upon P1. P external and P2 are same 1. P1 is 10, so it is N is 1 mole, so it is RT 1 minus 1 by 10, so it is 9 by 10. So 9 by 10 RT. So delta S surrounding will be equal to how much? Minus Q system by T. Minus Q system is minus 9 RT by 10 by T. So TT will cancel. So it is minus 0.9 R. So now we can see that delta S surrounding is different from delta S system. So delta S universe will be equal to delta S system plus delta S surrounding, which is 2.3 minus 0.9 R. So it is 1.4 R. Now if we substitute the value of R 8.314, we will be able to determine delta S of universe. So now we see that delta S universe is greater than 0. The process is spontaneous. The process is spontaneous. So be very careful in determining entropy change for system and surrounding. Moreover, delta S universe for all irreversible processes is always greater than 0, is always positive. So we can say that all irreversible processes are spontaneous. There is one more case in which entropy is determined so far as IIT JEE syllabus is concerned. So let us talk about that concept. Entropy change at transition point. What is this concept? Let us try to understand. Suppose we take a case of water which is liquid at room temperature, and its normal boiling point is 100 degrees Celsius. So if we convert water to water vapor at exactly 100 degrees Celsius and 1 atmosphere, which is the transition point of water at which phase change takes place from liquid to vapor state. if we boil water at 100 degrees Celsius, then all heat given to the water will be utilized in evaporation, will be utilized in vaporizing water, because we are not allowing the temperature to rise. So heat given will be utilized in doing evaporation work. For that purpose, that evaporation must occur very slowly, reversibly, so that system absorb heat but temperature does not rise, and heat absorbed is utilized in doing work of evaporation. In that case, we can say that the entropy change, which will be entropy of vaporization, will be equal to Q by T, since heat is given reversibly, temperature is not allowed to increase. So all change at transition point, at transition temperature, must occur reversibly. So evaporation, boiling, occur reversibly at boiling point exactly. And now this Q is nothing but enthalpy of vaporization of water, and T is nothing but normal boiling point. Boiling point of water. So if we know the enthalpy of vaporization and boiling point of any liquid, we can determine entropy of vaporization. So suppose we have been given that enthalpy of vaporization of water is 40.2 kilojoule per mole. Determine entropy of vaporization of water. It's a very straightforward question. So delta S vaporization will be equal to enthalpy of vaporization divided by TV naught. Enthalpy of vaporization is 40.2 kilojoule, so we convert it into joule, divided by boiling point. For water it is 373 Kelvin. So if we solve it, it comes out to be 107.8 joule per Kelvin per mole, and that will be true for any liquid. So now we can say that entropy of vaporization of any liquid is equal to enthalpy of vaporization of that liquid divided by boiling point. This is not true only for vaporization, boiling. This is true for any phase transition, like in case of fusion. In case of fusion, we can say that entropy change of fusion is equal to enthalpy of fusion divided by melting point. Similarly, for any allotropic change, delta S, allotrope, will be equal to delta H of allotropic change divided by T transition, which is transition temperature the temperature at which allotropic change occurs. So in this manner, we determine entropy change in different physical processes: expansion, compression, vaporization, melting, allotropic change, and so on.